Hello everyone, welcome to this video tutorial, and today we're gonna try to predict and analyze the static bending behavior of an hyperelastic soft material pneumatic network. And today we're going to use Abaqus for this simulation. The version that I am using is Abaqus 2018. As far as my experience and tests that I made with this kind of simulations, you can use above Abaqus 6.14-5 and it's going to work. I'm not sure if it's going to work with previous version of the 6.14 or if it is going to work with above version of 2018. I never tried, so I cannot really 100% assure it. So we are going to start this with creating a new model. I usually never create model with this pop-up windows. I always close this usually and I go directly to the model, or I create new models and I define specific my properties. So for this case we are going to use the standard explicit model for this tutorial, and then as you can see here, the new model database has been created, and the new model, the model 1, this is the standard name nomenclature for the new models, is also being created. If you click here, you can see that this is a standard and explicit, and usually I leave everything in default. If you know how to define, or if you are an expert user and you know how to define the properties here in this video tutorial, we are not going to, it's not in scope, you can modify them. Otherwise, for this tutorial, I really recommend you just leave it as default as it is. One of the most important things in Abaqus, and I would say in any simulation or finite element model simulator package, is to define the working directory. This is important because you don't want to have files, or you don't want to be missing files, or you don't know where the results transferred. So that is always a nice practice to define. And how do we do it in Abaqus? We define here a set work directory. In set work directory, I will define here, I have already a new directory, tutorial, and then let's say that we have here a new folder, and then is tutorial live. We select this and then press OK. The new directory is already defined, and then we click OK. This is going to help us to all the files that are going to be generated from this setup are going to be saved there. So how do we start this tutorial? And a little bit of a background history. As we say, the objective is to predict and analyze the static bending behavior of an hyperelastic soft material pneumatic network. If you are in the branch of robotics or soft robotics or additive manufacturing, you probably heard about this. And if you are really dipping into this simulation, into this video, probably you know what I'm talking about. And a little bit of the background history is that I will try with this tutorial and with you together to show how this simulation of an hyperelastic material, including large deformations, it works, how it works including these large deformations. And that is the objective for today. A little bit of the outline that we are going to give today for this video. The workflow is going to be structured, or the video is going to be structured in few different zones. I will try to mark in YouTube the different chapters, so you can always go back and take a look to exactly what you need, or exactly the point in which you are working now. And I'm going to do my best to edit those parts. So this is going to be, as you probably know already, Abaqus, you have here your different properties for the setup that you need to define. Usually we're doing it step by step in order to not get lost during the process. And we are going to start with the path, with the importing, or with the creation of your 3D part, and then we are going to go to the material section, in which we define materials properties, and then we are going to create section and define sections, assigning them to the materials that we create them. And then Abaqus works in kind of assemblies. We are going to import the instances, then we're going to create the simulation steps, And then if we need or if we want interaction, we are going to define interaction. For this case, we are going to define interaction and interaction properties. And then boundary conditions are going to be defined inside the steps. And at the end, we're going to talk about a little bit about how to run the job, how to create and define the job, and how to run it and execute it. And if we still have the chance, at the end, we're going to analyze the results, probably yes. And I'm going to give a quick overview how to analyze the results that we output from this simulation. So we're going to start with the paths. I usually always import path to Abaqus. To be honest, I never create paths in the engine, in the model and 3D modeling engine of Abaqus. I always import them. And I always usually import as well in step files. If you need some different files, you can choose from here. I usually import them in step. And I will have here a pneumatic network simplified for this tutorial. I will provide it in the video description, the file. When I import files, I usually leave this as default, and the attributes and the scale as well as default. If you need something else, maybe in the next videos we can talk a little bit about how to define different attributes to the path. So we click OK, and then the path is here going to show up. Yeah, this is the path. This is a very simplified soft actuator, pneumatic actuator with internal chambers, which we are going to try to, that in reality they are filled with air on the pressurization, and then it creates the bending behavior from one side to the other side. So I always use here to show it in parallel, and this is how it looks, the model. Yeah, we have these are the arguments, parameters or attributes for the path. We are going to take care of them right away. The second thing that we are going to do for this tutorial is to define the materials that we are going to use for the simulations. Materials, properties. For soft materials, there are some really good databases on the internet where you can find the material properties. But if you are in the field of soft robotics development, soft robotics research, there is not really that much of fixed defined material properties that you can use for simulation softwares. So here we are going to use the ones that we create in one of my research publications, and it's already tested, it's already proof tested, and it works. So at least I can give you that hint. And yeah, so we're going to start to define the materials. Materials is going to be defined right click or double click, it doesn't matter, double click for example. Materials, what we are going to use for today is a material provided from the company Keyens, and it is the name. You can Google it, probably maybe you know about this. And yeah, this is for a 3D printer. Actually, this is a 3D print. It's going to be a 3D printed material, and this is from the Keyens. We are going to define first step is we are going to define a general density property. This is really important. I think you cannot even simulate without it. Probably, I don't know. So density property, which is going to be uniform, and the mass density. One thing to think about in Abaqus is that in Abaqus you don't define units for all the properties that you are giving. You need to be like uniform in all the units that you are using. So here we are going to define a density of 1.049 E minus 9. As I said, we took this density out from tests, and we test everything. So this is a investigated density. Probably it's going to be similar around for different silicon materials. It's going to be around the same, in between 0.99 and 1.17 or something. Yeah. So then, very important, we need to define the elasticity, the elastic model for this material, and we're going to define elasticity, and then the hyperelastic model. As well investigated in one of my research is here. We're going to use a geo model to define the material, and then we're going to use coefficients, and this coefficients is going to be 0.1. These are, I think they are megapascals, yeah, and 0.02 for the C20, C30, and the other parameters are 0, so we don't need to define them. So these are the material properties that we calculate as well after the test that we made. I think we calculate like 0.019998 or something. We're going to put it in 0.02, and this, for this case, is enough. For this case is enough, and it's going to work, the simulation. If you have different material properties, you can as well use them, but for this tutorial this is going to work. So we click OK, and then we already have defined the material. The next thing that we want to do is to create sections. The Abaqus, in Abaqus you need to create section and define section and assign sections to the materials that you create in order to work with them. So we are going to go to sections. We are going to create a section 1, which is going to be, I don't know, silicon, for example. You have this pop-up window, and then it's going to be silicon, and the name, and then homogeneous, solid. Then we press continue, and then we press here we assign the material section to this section. We assign the material to this section. So if you can see here, we already have one section here, and is assigned to the material. And then if we go to the path, we have the section assignment tab. We double click on it, and then we select the regions to be assigned to as a section. We select the body, we click in done, and then we have this pop-up window with the section is assigned as well to the silicon section, with the silicon section assigned to the material. Here it is. So it changed its color, which means that it's already assigned to a material. Good. And then the next step in order to follow this tutorial is to create. I would really recommend, for the sake of simplicity and make an easy life, to define the surfaces in which you know that you need to work with them. For example, which kind of surfaces do we need for this example? We need the inner surfaces in the inner walls. If you cannot see them, I can my view code here, and I can view code manager, and I think we have epsilon, probably, yes, epsilon. We change them here, and as you can see, these are the inner cavities of the pneumatic actuator. So these are the surfaces in which we are going to apply the pressure, or in which the pressure is applied when you fill it with a fluid. In this case, usually we use air in the soft robotics research field. And yeah, so these are the important surfaces, the ones inside. And other important surfaces probably is these outer walls. This one here is because they are going to be the ones mainly expanded that after the pressure is applied. So I already, as I already said, I recommend you to create surfaces. So let's do create surfaces. To create surfaces, we go to the surfaces tab inside the path, and then we double click on them, and then we set the name of inner walls, for example. Click continue, and then it says select the regions for the surface individually. So if you have not really that expertise in Abaqus, this in the beginning this can be really painful, because you need to select them all, or you need to select them and then maybe you miss one, and then you deselect everything. So I recommend you just take your time, and I can really recommend you as well take one perspective in which you can select all in once. To select them continually, I forgot to mention that you will need the shift key, and then we just keep selecting the ones that we need. I think that was, yeah. So then we rotate a little bit, and then we have we can view the other ones. So we select them, yeah, and then don't forget the bottom, yeah. and we have the one here up. So let's take them as well. Let's select them. Let's move. And let's then select the other ones. That should do it for this side at least. Yeah. What I can really as well recommend you take a breath here and then just click and done. We still need to have the other side, but take a break. Otherwise, you maybe click something and then you will lose it. And by experience, I lost the surfaces. I cannot even count the time. So let's click in done. And if you go here, you can already see the inner walls that are as surfaces. But we need the other side. So let's click here. We have already the other side. If we click here, we can see that they are not selected. So let's go double click in inner walls again, and then press again here, and then we have the other side of the surfaces of the inner cavities. So we select this again, and I think that's all. No guys, we forgot this. As I said, yeah, we need to really take a look to which are the surfaces that we need and are important for the simulation. So these are the upper walls inside the main channel. So I think it's already everything selected. So we click done. We leave this, we close this, and then if you see the inner walls, it looks and it shows like everything is here selected. So it looks good to me, I guess. Good. And then let's create the outer walls. So let's go double click on surfaces and then outer walls. Let's click continue, and then we need to select them individually again. So we have here a view of most of them in this perspective. Just shift and click, left click, normal click. That's all. And then let's rotate. To rotate that smoothly, and if you select one wrong, you just need to go to the control key and then normal left click, and it goes deselect. And to rotate so smoothly, I use a 3D mouse from 3D Connection. And with mouse and keyboard, it's not more difficult actually if you have the experience with the keyboards, but maybe you can lose one surface or something in the shift control alt to rotate in Abaqus. But yeah, so let's click in done, and then we have the outer walls also created as surfaces. Good. So that was the next step, and then next step is to mesh the part. Mesh for this kind of large deformation simulation is it's not complicated. You just need to know which properties usually are the ones that works, or which kind of elements and which kind of mesh type do you want for this kind of simulations. So this is the mesh tab. Just double click. We were here. Yeah. So let's click now in the mesh. So now we're here, or you can go here to mesh directly. Yeah. So I usually mesh the parts individually. You can also mesh in the assembly as instances. I don't do that. I always mesh individually. It worked for me, and I do it like that, and it works. So to mesh for this tutorial, we are going to first of all to define the mesh controls. For mesh control, we are going to define tetrahedrons, or TET in this case is showed, and then just click OK. As you see, it changed color. Select the entities to assign mesh controls by, and then you click in the body, and then you press done. And as you see, it's already here defined. Press OK, and then here you can already press this X because it's already assigned to a mesh control. And then this is very important, and otherwise probably it's not going to work. This tutorial, at least, we are going to the mesh here tab, and then we go to element type, and then select the regions to be assigned as element types, and then we click in the body. Let's click done, and then this window pops up. Here we are going to use the family of 3D stress. We are going to use standards as the same as our model. Geometric order, we are going to use quadratic order, and then here we are tetrahedrons because we already assigned the mesh control, and then we are going to click in this hybrid formulation. And at the end we have C3D10H, and this is a 10 node quadratic tetrahedron. It's going to be hybrid, and it's going to be to a constant pressure. We click OK, and then select the regions to be assigned as element types as well here, and it's already assigned. Well, let's click here or escape. So now, in order to mesh the file, to actually mesh the path, we already define all the properties: element type, mesh controls, global size. So we need to actually click here in mesh path. Mesh path, okay to mesh path. Yes, it's going to take a few seconds and to mesh the path. This path was meshed with a global size of 1.5. I just want to show you the difference about the size. Why? Because if you have a approximate, we defined before a global size of 1. We mesh the path, and then this is going to give us a meshed path with about 260,000 elements. So this is the path, this is the mesh that we have, and which is 263,908,000 elements. This is not really heavy intense in regarding computational performance, but this is going to require at least a computer with 16 gigs of memory RAM. If you don't have 16 gigs of memory RAM, at least in your computer, we need to decrease the global size. With this global size of 1, I recommend you personally at least 20 gigs of memory RAM, because only the process that is going to take to solve this setup is going to take 16 gigs, plus your operating system, plus any other background process that Windows is always executing in the background, is going to take more space. So I can recommend you, if you have 16 to 20 gigabytes of memory RAM installed in your computer, go to a global size, a mesh global size of 1. I really recommend this, so you got better solution. It's going to be computational wise heavier to compute to get the solution, but this is going to be more accurate. And as I said in the beginning, it's not a good practice to try to simplify or to get faster results of something if you still have an accurate solution, or a more accurate solution in which take as a reference. If you can compute this, maybe take hours, but at least you know that it works. After that, you can already decrease mesh size, and you can keep it optimizing the solution time. Yeah, but optimization, you cannot optimize something that you still don't have and you still don't know. And if you mesh in the beginning with a poor global size, or maybe here is a, I don't know, let's say a 3, we mesh again, maybe you missed something in the results. Maybe the bending behavior of this is not going to be the same because you have bigger parts that they doesn't bend properly, and at the end you miss few millimeters in the results, which is going to just increase the error that you have at the end against reality. That's what I recommend. If you have at least 20 gigs of RAM, 16 to 20 gigs of RAM, go to global size 1. If you have below 16 gigabytes of RAM, go to global size 1.5. Yeah. So let's go back again to 1. Apply. Okay. Mesh the path. Yes. And yeah, it's a quite not complicated, but it's a quite interesting topic, to be honest. Mesh optimization for finite element simulation. So this is how it looks, the mesh. We have 260,000 elements, and it should work good with this. So let's go to the next step. That was the next point on the simulation steps. And then the next thing to do is to import everything to the assembly. As I said, Abaqus runs or execute jobs in relationship with the instances that we have. Even if we define here our path, if we don't define the instances, Abaqus is going to show an error that there are no instances to work with. So we are going to go to the instances, double click, and then create instance as a path. we have the path, which is this one here, and let's click OK. I always do the dependent mesh on path. As I said, I always mesh on path, and then it's going to be dependent. If you mesh on instances, you can make it independent, but then you need to mesh on the instance. So I leave it like path. We select all paths, usually it's always selected, or if you have more paths, usually they are already selected. And then we go to instance type dependent mesh on path, and then click OK. So now we have our instance, and here you already have as well your Cartesian, your coordinates, your main axis system, and it shows you in which directions you're working. As for the example, we are going to take the C direction as as set positive, and then it's going to be to end like this to C negative. And the main displacement is going to be in X, theoretically, or not, theoretically, should be no motion in Y, in epsilon, but of course in reality it has. So the main motion is going to be in X and in Z, and in Z. So let's do that. Then the next step is going to create the steps. Abaqus works in a step, and because this is an static, only structural mechanics simulations, we have the simulation steps, and we are going to have only one. Usually we have only one simulation step, but for the sake of a little bit more of accuracy and really to try to simulate how this works in reality, we are going to add the gravity step. We are going to add a first step, which is going to be taking care only on the gravity, because this is a really soft material. Usually when you hold the actuator from one side, it's already going to bend just because of its elastic properties. So that's the first step that we are going to simulate, and after that step we are going to simulate when we apply pressure. So then we are going to go into the steps. The initial step, I never touch the initial step, to be honest. I always leave it there, and I have quite experience in Abaqus, and I really always leave the initial step like is there, and I never had problems. But because I never had problems, I really never did research on the initial step, and I never delete it. I just leave it there. I can really recommend you, as my experience is already, I don't know, maybe 10 years in this software. You just leave it there, and as we engineers says, if it works, don't touch it. So then we create a new step, double click in the new step, or you can always right click and create. So then we come with this pop-up, and then we have, I always, for example, the name is going to be gravity, insert new step after the initial step, and then it's going to be static general. We have this description, we have no description. This is very important. We are going to activate the large deformations, nonlinear effects for this case simulations, and this is very important. If you don't activate this, it's probably not going to work. We are not going to use a stabilization automatic, so we just leave it like this with this in on. For the steps, incremental size, I will say if you put the initial step as 1, initial step, you need to you begin in 0, you start in 0, and then the end of your step is going to be 1. So if you put initial step 1, it's not going to work, at least with this increment size. So what Abaqus does is going to decrease the increment, the step size, and then it's going to do a new iterations for a lower step size. So I always can recommend you, probably if you have nothing, like really no forces in the step, you can do it in 1, otherwise go low. And Abaqus static, if you don't define another artist default, is going to automatically decrease the increment size or the step size in order to compute or to converge. So we are going to put it in 0.1 as initial, so it's going to start from 0 and then 0.1, and then it can increase or it can decrease depending if it reaches convergence or not. In this case, 0.1 is a good value, and then we leave it like this. In other, we leave it in default. Incrementation is automatic as default, 0.1, and okay. So we have the first step, and then in the first step we already have 2 boundary conditions that we need to address. The first one is going to be Okay, to add boundary conditions, you double click, or as always, right click on create boundary conditions, double click, and then we have this window pop up, and I will here create something that has fix end in order to fix or support. Yeah, otherwise it's just in the air. And it's going to be a fixed end in the step gravity. It's going to be asymmetric, antisymmetric, or encastre. This in this case. We click on continue, and then it says select regions for the boundary conditions, and this is going to be my face that I want, or the surface that I want, and I click done. And if you can see the boundary condition here, you can select the degrees of freedom that you want to kind of block. It's not like disable, it's like block. You don't allow the degree of freedom. I mean, yeah, it's not anymore a degree of freedom. So we put it in encastre, in which all the degrees of freedom are kind of equal, and block equals 0. So it allows no motion in any direction. Now we have usually these 6 degrees of freedom, which is X, Y, Z, and rotation X, Y, and Z. So we block them. So it's going to be U1, U2, U3, rotationals for each U is equal to 0. We click OK, and then now it shows like it's kind of here like a fix, no? Like it's not going to move. So that was for the boundary condition for this step, and then we need a load. Yeah, we need a load. Which kind of load, you ask? Is going to be the grav forces, the gravitational forces. I will just put the name here. And then it's going to be in the step gravity, it's going to be mechanical, and very important, we need to define it as gravity. Type for selected step gravity force. So the gravity forces is going to be in the component drive, in the component 3, sorry, which is in this direction is set, also vertical is set as we can see here. So it's going to be minus 9,810, which is the gravity value in the units that we are using. I recommend you to if you follow this tutorial with the same unit that I made, that I use, this is going to be the value that you need. Amplitude is going to be ramp as default, and then we just press OK. As you can see, now the load is created and it looks in the right direction. As we said, this is going to be bending in, hopefully, in this direction, hopefully for you as well, and it works. So that was for the step gravity. And then we create a new step. We go again here and then create a step, which is going to be press for the applied pressure. And it's going to be new step after gravity, which is going to be as well static and general. Incrementation and large deformations are already activated and propagated for the next step. Incrementation here is very important because, I mean, maybe in the next video we can talk about step size for simulations and yeah, the increment size, but here I will recommend a low value, because you need to imagine that if you already compute the gravity step, if you try to pressurize the network with a really huge step, like 1 second, it's going to try to simulate from this point in which already gravity is applied to the end, which is a lot. And the mesh, even if we have a really small mesh, you cannot really compute the in-between steps, and the mesh is really highly deformed, and the elements are going to be highly distorted if we have a huge step. So I really recommend a step probably 0.001. If you can compute this, then this is some good minimum value. Of course, then you need to imagine that to reach 1 second, you need 1000 steps, which is kind of heavy to compute. But Abaqus in static, structural, and in this in standard and explicit model is going to compute. If this work is going to try to increase the step size and then compute again. If that one also works, it's going to increase the step size and so on. So it's going to be really, like, it's going to try to make it as fast as it can. If you really care about to analyze each step in a defined time period, like if you always want to analyze at 0.001 seconds, always the same step size, then you need to define maximum as well, 0.001 for example. And then you are going to finish the simulations, you need 1000 steps. In this case, we're going to put maximum 1. And as I said, then automatically it's going to try to increase and decrease to make it faster, to compute faster. And of course, if we cannot compute here and we cannot compute there and the next one, and then we cannot compute until 0.0001, it's going to abort because of convergence failures. So we click OK, and then we have here one load. If we see, we have already one load and one gravity boundary conditions, which are the ones from the step gravity propagated to this new step. So this is very important. We don't need to define them again. And with this, we prove that the gravity forces are going to be applied in the whole model during the whole simulation period time. So we create a new load, which is going to be here, double clicking loads. We have a new load, which is going to be, I don't know, air press, I'm going to call it, and this is going to be pressure, mechanical pressure. And then here we have select surface for the load individually. We are not going to do this because we are already clever enough. We create surfaces. So we go to surfaces. We can see here that we already have the two surfaces that we previously defined in the part instance, and we have where do we want to apply the pressure? In the inner walls. So we select the inner walls, and then highlight, and then the magnitude. As we are, if you have a little bit of experience in these soft pneumatic actuators, they work around maybe 0.1 bar to 0. I don't know, maybe to 1 bar in the range. Bar is just because of the manometers usually are on those units. Here in Germany, we really don't use them, but I will say that in bars to kilopascals is like 0.0. I don't know. Let's define 30. This is like 30. This is 30 kilopascal. This is 0.3 bars, and 30 kilopascals, 0.3 bars, and 0.030 megapascals. That's why. But this is 30 kilopascals, 0.3 bars. It's pretty tricky, to be honest, if you are a beginner in Abaqus to work with the units. But with the time, you just get used to it, and you already know the equivalence in the units that you are working on. So this is 30 kilopascals, 0.3 bars. Good. We press OK. Very important. We go again here. We press OK. This is going to be ramped. Going to be ramped means that in the 0, or in the beginning of the step, which is 1.0, because we compute gravity, it is going to be 0. And then as we increase the steps, we go in the increment size for the steps. Pressure is going to be increase as well. And at the end of the pressure step, pressure is going to be maximum, which is going to be 0.03 megapascal, 30 kilopascal. You can define differently. You can create your own equations. You can make sinus, whatever you want. For this case, we're going to leave it as ramped and as default. And as we can see here, we already have the pressure applied in normal directions to the inner surfaces, to the inner wall surfaces that we define, which is good. We press OK, and then we have already the air press created. And that was most of the complicated things of the simulation to set it up. What we need to do as well is to create interaction. Interaction contact is in between these phases, because if you already have tested or you already investigate a little bit of this soft pneumatic actuator, when they expand, usually these outer walls they expand as well, because the air is expanded in the inside, and every outer wall is obviously expanded in the outside. So probably they are going to have contact when they are really high expanded. And if they have contact, we want to know, and we want to compute this contact as well, in order to predict maybe failures or too much contact that can lead to a failure, or just to really know when they have contact with the force. So I really recommend you to always try to define interaction properties properly. To do that, we go first to the interaction properties. Quite tricky because we have interaction properties. I usually always define interaction properties before, and then it's going to be, I don't know, maybe walls contact, which is going to be contact, and then we press continue. We have the contact property. For this case, and just for easiness, we are going to put them tangential behavior, and then they are going to be frictionless. Of course, you can here put a penalty, friction, and you can define even frictions coefficients of everything, and it's going to be of course more accurate for this, but more complicated as well. So for this case, tangential behavior, frictionless, we just want to have the interaction there and the contact. So then we go to interaction, and then in interactions we have the outer walls contact, for example, and here are different methods. I always use the self contact for this kind of. You can also use surface to surface. It makes probably more sense as you think about surface to surface. That's usually what you have. Yes, but self contact works pretty much as well, because we already define all the surfaces, and they can have self contact in between them. So we are going to use self contact for this case, for this tutorial, and then we are going to select the outer walls that we already predefined, and we leave it as default, surface to surface 0.2, and just as default. And then we already show here the contact, the self contact in between the surfaces, which looks pretty good. So that was for the setup scenario, and then we are going to the we can save it. Actually, we can save it. We didn't save it this whole time. Good. That's not a good case. I recommend it to save it. Probably I will edit the video and then tell you save it before. So we go to tutorial live, and then we go to tutorial revision 00. Good. Now it's saved, and you can see it's saved already here. And then we go to the jobs. This is already done. We went through a lot, step by step, through the whole simulation. And then here we are going to create a new job. To create new jobs, as always, right click create or double click. So we have the job, and then we put it here. 30 kilopascals. I can always recommend you to define your main load as I know something that indicates you which job you are running, and to use it in the future to not confuse or to not run it again with the same parameters. 30 kilopascals, revision 00, for example. In the model is going to be the source, and then this is the model one, the one that we here have. So we press continue, and then this is kind of important if you know a little bit, not computer science, but if you are a normal user, you usually are working in a workstation, in your personal computer, I don't know. And the most important of this job arguments is the parallelization, probably. This can really help you to speed up the simulation, the execution time, the solution time, to get the solution time lower. So here I usually always recommend to use multiple processor depending on the machine that you are working on. Usually, I don't know, if you have an Intel Core i7, you have 4 cores, 6 cores, maybe 8 cores, 10 cores. And yeah, the important thing here is that Abaqus can use the physical cores. So for example, if you have 4 cores and 8 threads, which is with the hyper-threading option activated, Abaqus does not penalty. Actually speeds up a little bit when you use hyper-threading as well. For example, if you have a 4-core CPU with 8 threads, you can use the 4 cores because those are the four physical real cores that you have, and it's going to work. If you select 8 here, it's going to take the hyper-threading cores as well, the ones that you see usually in the task manager when you press logical cores. I can show you here in mine one, for example, my computer which I'm working for, I have 36 physical cores, and I deactivated in my BIOS hyper-threading. I don't use hyper-threading personally, because this is because of the software that I use. Abaqus, as I said, Abaqus does not penalty you for using hyper-threading. Select the cores that your machines can allow. if you have 8 threads, you can select 8. You just need to take care that your machine is going to be kind of not very responsive during simulation times, during the job execution. Yeah, so I will select 36 because because this is my maximum, and I will just leave the simulation running for you. And this is a very important as well to check. Use GPU acceleration. GPU accelerations, Abaqus can take advantage of the graphics card that you have in your computer installed to try to accelerate the job. We can talk more about this in next videos probably. If you have a graphics card which is, I don't know, good enough, maybe you have at least 4 GB of dedicated video memory. It doesn't matter if you have an NVIDIA or if you have an AMD card. If at least you have 4 GB, usually good will be like 8 GB, 6 GB at least. 6 GB at least, that will be perfect for this case. You can use it as well. This has a lot of dependency. If you have that much cores, then you are not enabled, you do not allow the CPUs to parallelize correctly. Yeah, it's a pretty complicated case. If you have a dedicated video card, graphics card with 4 GB of more, I can really recommend you to check this box and activate it. It's going to really speed up your simulation. Even if you have a gaming graphics card, it's going to speed up. Maybe not that much as Quadro double precision capable graphics cards or Tesla graphics cards or Tesla compute cards. But even if it's going to work, even if you run in single precision mode, as we are doing here, it's going to work. It's going to speed up your simulation. The graphics card, as I said, as much as cores you have, if you have an 8 cores machine, 8 cores. If you have 12 cores, 12 cores. And if you have a graphics card with about 4 GB of dedicated video memory, you can as well select this. In my case, I have 2 GPUs. I have one NVIDIA Titan Black, and I have one NVIDIA Tesla K40. So I really try to speed up my simulation as much as I can. And then press OK. So as we see now, we have the job created here. If we click as well in the job, we can go again to the properties that we define. And I can really recommend you as well to save it again before running something. And if we made no mistakes during this tutorial, or if you get an error, you can go back to see the chapters that I'm going to define for you in the video. And then you can take a look what is probably wrong. And then I always recommend to monitor the solution. And yeah, with the monitor, you can see the status of the running job. And then let's press submit. And as you submit the job, it's going to first analyze the setup or the input file that we create in these all steps. Is going to analyze them and create a job file. And after that, it's going to start the simulation, the computation part of the job. As we say, it's already submitted for an analysis. Then it's going to start to, as I say, to analyze all the setups, and then it creates a job file. This job file is the one that is going to be executed or solved. Maybe the one that is executed is actually the input file. So let's wait a little bit, and after the job is running, I will just fast forward the video until the solution is done, and then yeah, see you probably for the results. But until it's not running, I'm going to stay here and take a look if any warnings, errors, something is coming out here. For this model, should be no warnings, should be no errors, and yeah, it should run smoothly. As we see here, the graphics card was already called to run the job as well, and we can see immediately how the memory is fully used. Abaqus is going to fully utilize the memory that you have available in your graphics card. That means that the simulation is running, And if we see in my, let's open here my commands window. If we see here, CPU is already working. 100% of my 36 cores are working on this. 100% of the GPU is also utilized. This is my Titan Black, which has also really good double precision compute capabilities. And if we check here, the NVIDIA machine is also using my Tesla K40 is using 12 gigabytes of my Tesla K40 in order to accelerate the simulation. So this is going to take a little bit of time, people. If we can see here as well, compute 0. This is the computing part that the NVIDIA is doing. The Tesla is doing exactly the same, probably. Maybe a little bit less of computer stress because of the compute capabilities of the Tesla. But yeah, so which means that it's working. The simulation is going to take its time. Don't worry if you don't see here in the monitor the update, make no worries. But as I said, you need to go here to the stat. I can recommend you to see the stat files, which is still not created. The stat file is going to be created as soon as the first increment size or the first step size is computed and solved. So yeah, I will accelerate this until the status file is created. So now here is the status file. This is already being created. If we double click on it, it says that the first step size at 0.1 is already being completed. It's already been computed and is complete. As I say, I'm sorry if this is not working for you. It's not working for me. But I say Abaqus, when you get really complex with Abaqus, and I perform a lot of simulations during the time, and here my time, so I don't know, sometimes operating system get messed up with software, and yeah, this start to happen maybe, I don't know, maybe 1 month ago. It's the start not working, but you can always take a look here. It's quite a pity, to be honest, but you can always take a look to your CPU. If it is loaded, it means that it's working. In this case, it's working. If you are using a graphics card and the graphics card is still loaded, full loaded, it means that it's working. Memory RAM is working. Otherwise, you can also go directly always to the app, and you see here how standard Abaqus is working. It's using around 16 gigabytes of memory RAM. If you don't have this enough memory RAM on your machine, we need to reduce the mesh. We need to reduce the mesh size or increase the mesh size and reduce the elements that we have at the end. But this is working. See you in the end of the simulation. As we see here, the simulation is working. As I said, it's perfectly working, and it's already in the time in the step. It's in the first step at the increment 2, which is the time of 0.2, because we define the step size for the gravity step at 0.1. So it's going to be 0.1, 0.2, and if it still compute this, it's going to increase probably. We don't know to which percentage is going to increase. Abaqus does that automatically if you don't know define it. So let's keep it as it is. So hello again. I think simulation has finished. As we see here, the CPU is not loaded anymore. System memory is also going down. The graphics card is also, the memory is also freed up. And as I told you, the simulation here was not even showed up, but if you check the message file, the analysis has completed successfully. We went from step 1 time 0.1 to we finished this step 1 at time 1. We start this step 2, and then we finished as well. So it's done. Here even Abaqus even showed about it. I have no idea why. I think maybe it was because I recently upgraded my operating system. That maybe can be the reason to Windows 10 Pro for workstations. And maybe that messed up something about because there is a lot of background services deactivated in this version of Windows, and I plus deactivate a lot more from services that I don't need, and always mess with the performance. Maybe that can be the case. Doesn't matter. To check the results, we need to go click right here in the job and then results, and then it's going to load automatically this .odb. ODB, those are the Abaqus result files. Those are the important files usually if you want to take the simulation with you, and it contains all the information about the variables that you were computing. So, if you don't open it like this, right click results, we can close this, for example, again, we close it, we go output databases, double click, and then we go to the working directory in which we defined in the beginning of this video, and here we see the name of the job, which is 30 kilopascals, revision 00, but we see the ODB file, no? We just click OK, we open it. So this is how it looks. The file, this is the undeformed shape. In order to take a look to the deformed shape, we click here, plot deformed shape. And there it goes. People, if you were having problems to simulate this kind of actuators, and if you took your time enough to watch 1 hour of my video, so this is how it looks. Yeah, this is the deformed shape. What we want colors in our life, so we plot contours on deformed shaped. So this is how it looks. These are the stresses, the von Mises stress distribution zones, and if you have experience in this soft actuators modeling, you know how these are the critical zones in which the stress is higher, and is going to be the risk is going to be higher there to get broken, or to have a failure. So this is how it looks. As you can see, we define the contact of these surfaces, but as you can see, we didn't apply enough pressure. With 30 kilopascal is not enough pressure to have them in contact. But if you create another job with maybe 40 kilopascal, maybe you can have it 45 kilopascals, maybe you can have the contact, and it's going to expand of course, higher, and it's going to bend, to continue the bending motion. There are some research. You can find that even the actuator bends all the way until here. Of course, everything depends on the parameters that you have of your geometry. So, for example, if we want to analyze a little bit, if we want to take a look to what is happening inside, we go again to our old friend, the view cut manager, and then we are here, and then we cut as well in Epsilon. And then we cut the other one because I am in this side, and this is how it looks from the inside, people. So this is how it looks from the inside. These are the critical zones as well. The mechanical pressure is applied to all these surfaces, and we can see that the critical zones are always the edges, and at the end the deformation was already transferred to the outer walls, and as well these are critical zones in which you can have failures. So this is how it looks at the end. I hope this helps you. If you have any questions regarding to the simulation setup, you can always contact me. I will leave my ResearchGate account. You can always leave in the comments any questions, and I will do my best to answer them, and I will do as well as to keep in touch with all of you that you have further questions. But this is how it looks, people. And when I learned this, when I started working in this topic, it was already like 3 years ago, more than 3 years ago, like almost 4 years ago. I had such a big time trying to do this kind of simulation. I spent hours, days of research, and you cannot imagine how much time I spent in the research of this whole soft actuators development. And if you took your time to follow this tutorial until here, maybe this probably helped you. And after this video, I can assure you that you are going to be able to follow up with your simulations if you need this kind of simulation tab. It doesn't matter if it's this kind of actuator. With this, I can show almost any hyperelastic materials with similar properties is going to work if you follow exactly the same procedure that we took in scope during this video. So thank you very much, guys. Please don't forget to subscribe. This is a new channel, and I will do my best to keep you posted with some new simulation techniques and how to go through them. Different software is going to be used as them, and expect for the next video how to follow this as well, probably with ANSYS, which is another very interesting piece of software to work with. Thank you very much, guys, and see you the next time.